Jai Hind, everyone. Myself, Dr. Pankaj Goel, working as Assistant Professor in Electronics and Communication Engineering Department at AKGEC Engineering College. Today we will discuss a very important topic of diffusion mechanism and doping profile. As we know that in a semiconductor fabrication, doping of impurity atoms is a very important step. There are two techniques by which impurities can be doped in a semiconductor wafer. These are diffusion and ion implantation. So today we will discuss about what are the various diffusion mechanisms in a diffusion of the semiconductor wafer. Before discussing the diffusion mechanisms, let us see what diffusion is all about. So diffusion is nothing but a movement of carrier from the regions of higher concentration to regions of lower concentration. And this movement of dopants from higher concentration to lower concentration is done at a high temperature in the range of around 800 to 1200 degrees centigrade. We have to understand the structure of the lattice to understand the diffusion mechanisms. So we can see here these circles which are hollow. These are the regular lattice structure atoms. Like if we talk about silicon semiconductor, then these hollow circles denote the silicon atoms. And these black holes, black circles which are filled with black color, these are the impurity atoms or dopant atoms. Now, also one more thing here, that these regular lattice atoms which are kept in a regular order, in between the regular atoms there is a space, vacant space. And if any dopant atom or host atom is placed in the vacant space, then that is known as interstitial atom. Okay, now with this here we can see that interstitial site is a position between the regular positions in an array of atoms. Okay, now let us see, if a dopant atom is placed at a regular lattice site by displacing a host atom, then this is known as vacancy diffusion. If a dopant atom is placed at a regular lattice site, then this is known as vacancy diffusion. This is one of the diffusion mechanism. Okay. So now, if the migrating atom is a host atom, then it is known as self-diffusion, and if it is an impurity atom, it is known as impurity diffusion. So vacancy diffusion is further, we can say, of two types, self-diffusion and impurity diffusion, depending on at the lattice site the displaced atom is the dopant or the host atom. The second kind of diffusion mechanism is interstitial diffusion mechanism. Now, what happens in this mechanism? If your dopant atom does not disturb the regular lattice atom structure but is placed in between in a vacant space, then this is known as interstitial diffusion. So this is second kind of diffusion mechanism. In another figure here we can see, this is known as vacancy diffusion mechanism. This is also known as, its another name is substitutional diffusion mechanism. So this is an example of vacancy or in substitutional diffusion. Here in the second figure, middle part, we can see that your dopant atom is moving in a free space in between the regular lattice atoms, where the free space is available. Dopant is moving in that free space. So this is known as interstitial diffusion mechanism. And there is another third kind of diffusion mechanism which is known as interstitial C diffusion mechanism. Now what happens in interstitial diffusion mechanism is that it involves more than one step. As we can see here, one of the atom is moving from an interstitial position to another interstitial position, that is in a vacant space, but it is not moving from one position to another in a single step, but it involves in between the displacement of many other atoms. So this kind of movement in which one of the dopant atom moves from one interstitial position to another interstitial position involving number of steps, then this kind of diffusion mechanism is known as interstitial C diffusion mechanism. Once again, we can see here, this is an interstitial atom, the atom which is kept in a free space between the regular atoms, that is a interstitial atom. And if this interstitial atom moves from one free position to another free position, but in that process it involves movement of or displacement of other atoms, then this is known as interstitial C diffusion mechanism. And if this interstitial atom moves from one interstitial position to another interstitial position directly, then it is known as interstitial diffusion mechanism. So there are three kinds of diffusion mechanisms: vacancy or substitutional diffusion mechanism, then interstitial diffusion mechanism, and then interstitial C diffusion mechanism. Some more information about diffusion mechanisms. The dopant atoms which are smaller than the host atom, that does not form covalent bond with the silicon atoms, they move interstitial way, because actually they are having small radii, so they can fit in the free space and they can have enough free space available, path available, where they can roam around without displacing or colliding with the regular lattice atoms. And another important thing about the interstitial diffusion mechanism is that it requires less activation energy, because in this kind of movement it is not required to displace a regular host atom from its position, so no collision occur. So if a dopant atom can move interstitially in a free space, then it requires less activation energy. So this is an example of interstitial C mechanism which involves 4 steps here. Here we can see that boron and phosphorus, these are our dopants. Boron is our trivalent impurity and phosphorus is pentavalent impurity. So these dopants has a property that they move interstitially. The dominant mechanism of diffusion in these kind of dopant is interstitial movement, whereas the arsenic and the antimony diffuse predominantly via vacancy mechanism, because they are bigger atoms, Boron and phosphorus, they are small, they have smaller radii, whereas arsenic and antimony have bigger radii. So arsenic and antimony diffuse predominantly via vacancy mechanism. Further, we can see that group 1 and group 8 elements having smaller ionic radii, small ionic radii, and they are fast diffusers in silicon. And they diffuse via interstitial mechanism. Now, the second part of our discussion today is about doping profiles. Now, doping profiles gives information about the distribution of dopants or impurities in a wafer. And there are two main doping profiles named as constant source doping profile, also known as constant surface concentration profile. And the second one is limited source doping profile. These are very important doping profiles. First, we will discuss about the constant source doping profile, or also known as constant surface concentration profile. As the name indicate, in this kind of doping profile, at the surface, the concentration is maintained up to a level which is known as solid solubility limit. As with the time, we know that in case of diffusion at higher temperature, the dopants or the impurities move from higher concentration region to lower concentration region, and we have maintained the dopant concentration at the surface. Now with time, as these dopants are moving from surface to the into the deep wafer, then the surface concentration is going to decrease if they are not given by the external source. So in case of constant source doping profile, we have an infinite source of diffusion. We are using an infinite source here which keeps on providing the, or keeps on maintaining the dopant concentration at the surface. As the dopants move from surface to deep into the wafer, the concentration of dopant is replenished by the source, and the value that is maintained at the surface is known as solid solubility limit. So, which is denoted by value N0. At the surface, the value of x is 0, and at x equal to 0, the concentration is equal to N0, which is the solid solubility limit. Now, at infinite distance from the source, the doping concentration will fall to 0, as obvious, because when the dopants are moving from higher concentration to lower concentration, so at infinite distance, the concentration will obviously be 0. So the concentration at x equal to infinity will be 0. Further, we can see that at t equal to 0, time t equal to 0, the doping concentration is 0. This is the initial condition. This is the initial condition. And the boundary condition are two, that at the surface, the doping concentration is equal to the solid solubility limit, and at an infinite distance from the source, the concentration is going to fall to 0. So there is one initial condition and two boundary condition which are used to find out the doping profile. And in this case, infinite source of diffusion case, we see that the doping profile follows the complementary error function profile. This is the doping profile in case of infinite source of diffusion. Here we can see that at all the time at the surface, when x equal to 0, the concentration is maintained at the solid solubility limit, that is N naught. And as the time increases, as the time is increasing, T2 is greater than T1, T3 is greater than T2, T4 is greater than T3. What is happening? The dopants are moving deeper into the wafer. More the time, more diffusion will happen. More the dopant atom will move further into the wafer. So, from this mathematical expression that is obtained for this infinite source of diffusion or constant source doping profile case, complementary error function doping profile is followed here. This is the mathematical expression where at any point x inside the wafer, the concentration is given by N naught, that is the surface concentration, multiplied by the complementary error function x divided by 2 raised to the power 2 under root dt. Okay, the second case is limited source doping profile. As the name suggests, in case of limited source doping profile, the source is shut off. That is, initially we have provided a concentration of dopant at the surface, and when the diffusion starts, the source of the concentration, dopant concentration, shut off. So it means with time, as the dopants from the surface are moving inside the wafer, the surface concentration start decreasing, as can be seen here. As the time increases, the concentration at the surface start decreasing. So this is your limited source diffusion profile, and this limited source diffusion profile follows the Gaussian function. This follows the Gaussian function. Okay. Now, one very important point that come here in case of doping profile is junction depth. We have seen this junction depth in all the figures here, and see, we have seen this in infinite source of diffusion case also. This is known as the background concentration. We can see here, this is known as the background concentration, and see. And when our impurity concentration at any point of time match equal to this background concentration, that point is known as junction depth. This can be understood with the help of an example here. This is an example of a CMOS inverter. Here we can see that if we have a P-type substrate and we have to create an N-well, then at the background we have a P-type doping already in the wafer, so that is background concentration. And at a certain point, when we are doing N type of doping to create N-well, at a certain point the P-type dopants and N-type dopants will be cancelling out each other effect and become neutral. At that point, that is known as the junction. Here we can see this is our junction. This is the junction, and this is the point where N-type dopants which are introduced by us, they electrically neutralize the effect of P-type background concentration. So that is the junction depth. That is the junction depth. So in this case we see this is junction depth. This is 0. This is xj. So this is our junction depth. Quickly Finally, I would like to tell you about the various diffusion system also. We have three type of diffusion system based on the source of the diffusion system. The dopants that we introduce into the wafer, it may be having a solid source, liquid source, or gaseous source. So based on that type of dopant source, there are three kind of diffusion system: solid source diffusion system, liquid source diffusion system, and gaseous source diffusion system. So this is the schematic diagram for a solid source diffusion system. Here in this case, the dopants are kept in a platinum source ball, and when it is given high temperature with the help of a furnace, then these carrier gases take away these vapors, high temperature vapors of dopants to the wafer or the slices which are kept here, and these vapors get diffused in these slices. Similarly, we have a liquid source diffusion system in which we are using a liquid source. Here the carrier gases are sent into this liquid source, which is given a high temperature treatment with the help of a temperature controlled bath, and these carrier gases which are saturated with these vapors now flows into the quartz tube where the slices or wafers are kept, and these carrier gases take the dopant vapors into the quartz tube where the diffusion happens. So this is a liquid source diffusion system. And in the last, we have a gaseous source diffusion system in which we are using a dopant gas. So carrier gases along with dopant gases that travel to the quartz tube where the slices are kept, and dopant gases are diffused. The dopants from these dopant gases are diffused into these slices. So these are the three types of diffusion system: solid source, liquid source, and gaseous source diffusion system. So today we discussed three topics. One is diffusion mechanisms. Second, we discussed about doping profiles, and the third is about diffusion systems. These are some of the important questions that may be important from examination point of view. The book that may be followed for this topic is SMG, VLSI technology from McGraw-Hill Education. Thank you.